All right. Great. So this is lecture 24. This is going to be about information theory. So information theory has a classic textbook by Cover and Thomas, but there's more modern stuff out there, which we'll talk about a little bit. And it includes a lot of nice works by Braverman recently. One more time. All right. Okay. So today's topic, information theory, there's lots we could talk about. I'm going to talk about some of the basics, just definitions about entropy and mutual information. And then we'll see one application, information complexity, that's an application to communication complexity. So I'm doing the application so that it connects with previous lecture. Okay, so let's start out with entropy. So all this topic, information theory, was developed almost in one shot by Claude Shannon in 1948. In particular, he gave this definition of entropy, which we're going to describe now. So let's start with an example. Let's say that x is a discrete random variable. It takes on finitely many values. So in this example here, x takes on the values red, green, blue, and yellow. And the probabilities are as shown up here in this example: half, quarter, eighth, and eighth. So first I'll tell you what the entropy of this random variable is intuitively. So the entropy is usually denoted h of x. It's a number associated with the random variable. And one way to capture it intuitively is to say it's the amount of randomness in x in bits. Another intuitive way to describe it is it's the minimum number of bits needed to generate a draw from x on average, if you're using the best scheme. So imagine that you needed to write a computer program that output draws from this random variable x with these specifications, and the only thing you're allowed to do is flip a fair coin. How many coins are you gonna have to flip on average with the most efficient program? This is what we're asking ourselves. So one scheme you can do for this particular x is first flip a coin, and if it comes up heads, you can output red, because red is supposed to come up with probability half. If it comes up with tails, then you can flip another coin, and if that one comes up heads, you can output green. So then green will, correctly be output with probability a quarter, and so forth. You can flip one more coin to decide between blue and yellow. And now we're going to compute, the expected number of coin flips your program used to generate this random variable x. Well, with probability half, you used one coin flip. It's probably a quarter, you finished in 2, and well, with the remaining probability, you finished in 3. So if you add this all up in expectation, you get on average 14/8 or 1.75 coin flips. Okay, so the entropy of this random variable x is going to be exactly 1.75. Another way to describe it is it's the minimum number of bits you need to store a draw from x on average using some kind of compression scheme. Actually, in many ways, there's not a lot of difference between communication and generation and compression. So you could use that scheme that we talked about to generate x and just record the coin flips you used and use this as sort of like a code by which to encode a draw from x. So for example, if you're trying to draw, encode draws from x, you could say, all right, red, I'm going to write down heads. Green, I'll write down tails, heads. Blue will be tails, tails, heads. Yellow is tails, tails, tails. And, in some cases you're using 1 bit. Some cases you're using 2 bits. In some cases you're using 3 bits to record this variable's outcome. And this is a nice example. The scheme here is what's called a prefix-free code, which means if you're drawing several instances of this random variable x and getting a sequence like red, blue, red, green, green, you can just write down these encodings with heads and tails with no additional punctuation in between them, and you can recover any sequence. So like tails, heads, tails, tails, heads, heads, heads. If you look back at this chart, it means first you flipped, let me get my little pen out. First you flipped green. The first draw of heads was green, and then the second draw was blue, so you wrote down tails, tails, heads, and then you flipped an H, got, so you didn't flip an H, but you got a red, and so you recorded it with heads. You got another red, but recorded it with heads. Yet another way to think about it intuitively is that imagine, your friend took a draw from this random variable x and got either red, green, blue, or yellow, and then you had to play 20 questions with your friend to determine, what their outcome was, red, green, blue, and yellow. And you had to only ask yes/no questions, and it would be sort of the minimum number of questions on average you would need to correctly determine what their outcome was. there's a question. Do you always mean, the question from the audience is, do you mean there's always a prefix-free encoding which is the best? Well, actually, there is always a prefix-free coding that is the best. And in this specific case, as we'll mention in a second, I chose an example which has a very special property, namely, all the probabilities are powers of, inverse powers of 2. In that case, the analogous thing to what I did for a general random variable leads to a prefix code, which is the best. When you don't have this powers of 2 thing, it gets more complicated. And as somebody else pointed out in the questions, the best thing you can do is something called Huffman codes, which we won't actually get into in this lecture. This is also a particularly trivial example because, like, if you think about this yes/no 20 questions version of it, then like the optimal strategy is kind of a very silly strategy where like the first question should be like, well, is it red? And if it is, then great. If it's not, then your next best question is, was it green? And then your next best question, if not, is, was it blue? But you can have a more complicated scenario with a more complicated random variable. So as I mentioned, yeah, so all of these, intuitive definitions of entropy that I've given so far are actually exactly, correct if X does satisfy this special property that all the probabilities are inverse powers of 2, like 2 to the minus k for some natural number k. Then all those intuitive definitions are exactly correct. And this would be the formula that you get. You just imagine, for example, the sort of the example we saw with the heads and tails. You imagine the expected number of coin flips your program would need to generate a draw from the random variable X. And you kind of go through each possible outcome, red, green, blue, and yellow. Those are the little x's here. And there's some probability that I've denoted P sub capital X of little x. So capital X means the random variable. Little x means like an outcome, like red, green, blue, yellow. And there's that probability that you would be trying to generate that outcome. And then the number of, coin flips you needed was like, the log base 2 of the reciprocal, right? So like blue corresponded to like, I don't know, tails, tails, heads or something. Corresponded to 3 flips, which is like log base 2 of the reciprocal of 1/8. So probably you've seen this formula before at some point. This is the definition of the entropy of a random variable X. It's given by this formula. And okay, we can imagine applying it to maybe a different discrete random variable X, like this one, where the probabilities are not like all like, negative integer powers of 2. So like, X is A with probability 1/2, B with probability 1/3, C with probability 1/6. Now, if you imagine like trying to write a computer program that, generated draws from this distribution X, or like you tried to, communicate a draw from this distribution to your friend by sending as few bits as possible. Well, things start out well with this probability of 1/2. With probability of 1/2, you can, communicate or store 1 bit. But then with probability 1/3, you would want to try to send or store or use like log base 2 3 bits according to the formula. And that doesn't really make sense because that's not an integer. So you don't have like a perfect correspondence between the intuition and this formula in case that, these probabilities have the property that like log base 2 of the reciprocal is not an integer. But, you just go with it. I mean, you just accept it. And so this is the formula that gets used for any random variable X. And then it doesn't have like an exact perfect correspondence with these intuitions that I've mentioned before, but they're good intuitions. In fact, we'll see in a moment how like you can make them even more precise, these intuitions. So just on the topic of this coding situation, like if you want to store like a bunch of draws from this random variable as bits, one thing you can do is just take the ceiling of all these quantities to make them an integer, and then it's okay. So like you could have a scheme for storing like say draws from X where you'll use heads to store A, and tails heads to store B, and tails heads to store C. And then it's a bit wasteful because you're not using the sequence tails, tails, tails for anything. But that's life. And this is a pretty good way to, compress a bunch of draws from a random variable into bits. This naive way of, I haven't exactly defined it here, but I sort of sketched it, is called the Shannon or Shannon-Fano code. And it's a pretty good scheme. As mentioned by somebody else in the chat, there's actually a better scheme that uses fewer bits on average called the Huffman code. It's sort of the optimal scheme in general. But you know, this scheme where you sort of just like pay up to 1 extra bit per draw due to the fact that, you know, these logarithms are not necessarily an integer is not such a bad scheme. So in general, how many bits do you use on average if you try to store your, you know, draws from your random variable or communicate draws from your random variable in this way? Well, it's sort of the same formula, except you have this like ceiling in here. And this ceiling is at most what you get if you take the actual, you know, real number and add +1 to it. And so if you look at this expression here, and like you break it up into its 2 parts, the first part, when you expand out, gives you the actual, you know, entropy term, this thing here. And then you get plus the sum over x of p of x times 1. So that's just +1. Okay, so overall, this simple method of encoding or generating or storing draws from a random variable x uses a number of bits, which is at most the entropy +1. Okay, so as always, if you have questions, do type them into the chat. Question is it hard to determine if a given encoding scheme is uniquely decodable? Whether it has the, well, these schemes we're mentioning like have like this property that's different from the situation when we're talking about coding theory. The difference is that the number of bits you use to encode a message or a draw is not always the same. It's like a variable length encoding. And there, if you're not going to use punctuation, then you need your, but you do want a variable length encoding, you need your scheme to have this prefix-free property where no code word is a prefix of another code word. That, of course, is easy to check if you have a whole list of code words. And if your code has that property, then it can be uniquely, and like a sequence of encodings can be uniquely determined, it can, you know, be turned back into, there's a unique way to break it up to get code words. Yeah, the question is non-prefix-free codes can be uniquely decodable. Yeah, probably, possibly. I'm not 100% sure, to be honest. Okay. All right, so this is the formula, and let's, if you haven't seen it too carefully before, let's go over some basic facts about it. So, okay, it's a number that's associated with a random variable that somehow measures like how many bits of information a draw from it carries. And so here's some basic facts. I'm going to ask you to fill in these blanks in a moment, so think about those. Let's say your random variable x can take on one of at most capital N values. Then it's a fact that this entropy is at most log base 2 of capital N, and it's always non-negative as well. So it's at least 0. Okay, so we can think about when these two inequalities are sharp. So feel free to type into the chat the situation, what random variables x have 0 entropy, and which random variables have log n bits of entropy, where n is a bound on the number of outcomes. Yeah, so a couple of people have said it correctly. That's right. So the first case, a random variable has 0 entropy if it's constant, if it's not really variable, if it's always the same value, or it has like a probability of 1 of some outcome. And has maximal entropy log base 2 of n if and only if it's uniform on the n possible outcomes. They each have probability 1 over n, and that's true whether or not n is a power of 2 or not. Good. So it's sort of the least variable and the most variable random variable. And there's a lot of, when you're proving things about like entropy and other elements of information theory, there's like a lot of like little exercises that involve like writing down expressions with like logarithms in them, and mainly using the fact that like the logarithm function is convex, or like the logarithm of a reciprocal function is concave, and using, you know, Jensen's inequality and things. So I won't prove it. I'll only do like maybe one of these proofs, but like the proof of this fact, the second fact, is an exercise for you using concavity. Okay, so let's go back to this slight annoyance where we saw that, like, let's say we have a random variable x and it doesn't have this, pleasant property that all the outcomes have a probability that's like 2 to the minus k for some integer k. And we saw that, like, if we want to, compress a draw from this random variable x, we could, invent like a simple scheme where the number of bits stored on average or communicated on average, if we're communicating it, was at most the entropy plus 1. And the plus 1's kind of annoying, but there is a way to get rid of it and to kind of get around this fact that, ultimately number of bits has to be an integer. And that's to think about the idea of amortization, or about like what happens if you're going to repeatedly draw from this random variable and store like many copies of it, or repeatedly get draws from this random variable and communicate it, and to think about like how many bits on average you have to communicate. So let me go into some more detail about that. So let's start with what's like a sort of simple fact. Let's say that x and y are independent random variables. So this independence is going to be important for what I'm about to say. So you can view the pair x comma y as itself as a single random variable. Okay, you just say, oh, I'll stick x and y together and call like that one object also a random variable. And it's often, or at least in information theory, often just denoted by concatenation as though it were a string, x, y. And when x and y are independent, it's not hard to check from the formulas that the entropy of the joint random variable x, y is just the entropy of x plus the entropy of y. And here's the intuitive proof of it. If you take the viewpoint that, like, okay, entropy is the number of, random bits you would need if you're writing a computer program to generate a draw from the random variable in question. Well, on one hand, if you want to generate a draw from this random variable x together with y, like one thing you could do is take, the most efficient program for generating a draw from x and the most efficient program for generating a draw from y, and like just run both of them. And now you've got a draw from like x and y independently, and the total number of bits you used on average was the sum of the number you needed for x and the number you needed for y. So in some sense, that's like an upper bound that would show that, or that would give a sketch of why we have the upper bound here. And as for the lower bound, just basically, if x and y are independent random variables, like there's no savings that are possible. There's nothing you can really do except separately try to generate x and separately try to generate y. So this is an intuitive proof, and like this is the kind of proof intuitions that like get you very, very far in information theory. Ultimately, you have to write down proper mathematical proofs, which look more like this. So as I said, I'm going to show you this one proof, and then I'll just rely on intuitions for most of the other facts that we talk about. Because in most cases, like these proofs are kind of like an exercise in like manipulations, and they follow the intuition. So we can, write it on the definition since we're doing, the first example here. Okay, so by definition, the entropy of the joint variable x and y is, well, you sum over all possible outcomes for this random variable x, y, which consists of pairs, little x and little y. And you get the probability of seeing this pair, little x, little y, times log of 1 over the probability of this little x and little y. And now we crucially use the fact that we're assuming the random variables x and y are independent in this story, which means that it means that this equality is true, that like the probability of seeing some little x and some little y is just the product of the probabilities, the probability of seeing little x times the probability of seeing little y. And we can also break up the sum into a double sum, because the range of possible values for this joint random variable xy is just the range of x together with the range of y. And then we use the property of the log function, that log of the product of two things is the sum of the logs. So we kind of made the same replacement about the probability of xy being the product of the probabilities here in this expression. And then we separated that into a sum. And then in this next line, I kind of ask you to imagine like, expanding or distributing across this sum. And you'll get a term that looks like the sum over x and the sum over y of px, py, and then log 1 over px. So if you put all that x stuff together, you get the entropy, the expression for the entropy of x, but you also have the sum over y where you're just summing the probabilities. But luckily the sum of the probabilities of y's is 1. Okay, and that gives you this term. And similarly, this second logarithmic expression gives you the entropy of y times the sum of the probabilities for x, and that's 1, so you get this h of y. Okay, so that is the formal proof of that equality. Okay, and you can iterate this, and so as a corollary, you get that, let's say you have n independent random variables, then the entropy of that single random variable that you get by like just treating them all together is the sum of the entropies. And in particular, if you have like one random variable called x, and you make like n independent draws from it, and thereby get like sort of copies, x1 through xn, independent copies of this random variable x, then the entropy of like all those draws together is just n times the entropy of like a single copy. Okay, so let's remember that fact. Because it relates to this amortization that we were talking about, like imagining, instead of storing or communicating or generating one copy of x, like let's imagine storing or communicating or generating like, a large number n of independent copies of x. So, okay, so let's say you were trying to store or communicate n draws from some random variable x. Well, one thing you could do is you could say, okay, I know like a scheme for communicating like one copy of a draw of x, and it used like entropy of x plus 1, in the worst case, many bits. So then if I need n copies, I could just do n times that. So the total number of bits I would get is n times the entropy plus n, which is okay, actually, but it is a little bit wasteful. So as an example, like let's say x is a uniformly random trit. It's 0 with probably a third, 1 with probably a third, and 2 with probably a third. So the entropy of that random variable is 1.6 bits, log base 2 of 3. You can check. And so this scheme that I mentioned here, basically uses 2.6 bits on average per trit. It'd be like it would encode like 0 with heads and 1 with tails, heads, and 2 with tails, tails, or something like that. And so overall, you'd be using 2.6 n bits on average to send n trits. You can see that's kind of a waste, because really, if you have n draws from this random variable x, it's like you're getting like a random number written in ternary with n ternary digits. So it's like basically a random number between 1 and 3 to the n, or 0 and 3 to the n minus 1. You should really be able to encode it with a number of bits that's like basically the log base 2 of that, which should give you this log base 2 3 per bit, like 1.6n bits. And so you see, using this corollary up here, you can do something different, at least in principle. You could instead say, wait a minute, like let's just treat this x1 through xn as like one single random variable whose entropy is 1.6 times n by this corollary. And now we could have a scheme for generating or communicating or storing a draw from this like n-fold random variable. And the number of bits we'd use would be the entropy, n times the 1.6, the base entropy, just plus 1. Okay, so instead of plus n, we got like plus 1 if we kind of batched these draws together into groups of n. And that's kind of cool because then if you, divided this quantity by n to sort of see the number of bits per batch that you, or per draw, I should say, that you used, it's like exactly the entropy plus, now instead of plus 1, plus 1 over n, which is tiny. It's like going to 0 as it's little of 1 as n goes to infinity. So by using a different scheme where you like group your draws together into big batches and encode them using some kind of binary encoding scheme like this Shannon Fano code, you can get into a situation where like the number of bits you communicate per draw of x, like in the long run, is asymptotically close to the entropy h of x. So this kind of shows that like h of x is sort of exactly equal to like the amortized cost of transmitting one draw from the random variable x if you're allowed to amortize over like a large number of independent draws. Okay, so this box, I guess, is what I just said.